All right, so now we're going to talk about covariant derivatives, in particular of a vector field. Okay, so let's consider a vector field. Let's denote that by x. So this is just a vector valued function on a manifold. And the value which at the point C, right, is given by the following, right? So you think of x, you evaluate it at a point, right? And so this is written as a vector, right? X super I, so it's like which depends on C, and then there's a basis which also depends on C, and this is in the tangent space at the point C to the manifold M. Okay. All right. So when you have a vector field, then it's like you want to evaluate this sort of change in the vector field. It's like as your base point changes. And it turns out that the way to do this evokes the use of an affine connection. So to measure the change of the vector field sort of as a function of the base point intrinsically, one needs to use an affine connection. All right. And in principle, that should not be too surprising to you, because our usual notion of things like derivatives involve taking this finite difference, it's like of the value of the function at two different points, then scaling it by the length of the distance between those 2 points and looking at the limit as that length goes to 0, right? So, but in particular, since this function in question is a vector valued function, you need to take the difference of two vectors but based at different points. And as we've talked about before, in order to make sense, in order to identify it's like the tangent spaces at two different points, one needs to introduce the affine connection. So the notion of taking derivatives of vector fields then very, very naturally it's like brings into play it's like this idea of affine connections. All right. So yeah, as a remark, right, affine connections are necessary. Right? Since we are comparing vectors based at different points. In order to construct this notion of the change it's like in the vector field, right? So in particular, right, I need to look at the vector field at a point, because C plus a slight perturbation, right? So the vector field at a nearby point, okay, which is in the tangent space to this base point, this perturbed point, and then move it, it's like to the tangent space at C. Okay, so given I want to map it to a vector in the tangent space at C. Okay. So in particular, because of the way we've written down, it's like this, it's like this vector field, it's like as a coordinate value, which depends on the position, as well as a set of basis vectors. We have to see how these basis vectors at the nearby point transform back to the origin, to the initial base point, right? And if you recall, that's how we introduced this affine connection, was to address exactly this question. So if you have this sort of basis vector E sub I tilde, okay, which is essentially E sub I at cos C plus D cos C, right? It is mapped to the tangent space at cos C by EI prime, right, which is EI cos C plus gamma, which are these connection coefficients, IJK, EK, D cos CJ, right? So this is telling you how, it's like a tangent vector. It's like it's like at a point cos C plus D cos C gets mapped to a tangent vector at cos C, right? Okay, so what that means is that if you have this vector field evaluated at cos C plus D cos C, and you want to bring it back, it's like to cos C, the value you get is as follows. So the vector x cos C plus D cos C, right, is mapped to the tangent space of cos C as, let's call it x tilde. Okay, so this is xk cos C plus D cos C. So I'm keeping the coordinate value the same, but I'm changing the basis vector, right? So this basis vector is E tilde I. Right, so this is sort of the representative of the vector field value at a different point. It's like, but expressed, it's like on this tangent space at the initial point. Okay. All right, so I can expand this, right? So because what I can do is that now this x super k is now just a scalar valued function. I can do a Taylor expansion at this, and I can write down the expansion of E tilde I. It's like given by this expression here, and then what I get is xk ek plus dj xk ek d cos cj plus the connection coefficients. Okay. So I'm just going to leave this coordinate change expression here. All right. So what's happening here is that I used a Taylor expansion of this term. So where we've Taylor expanded xk and used sort of this equation and dropped sort of the higher order terms. We're only looking at sort of the linear terms. Okay. All right. So now that I've done this, I can take the difference of this. It's like and the vector field at the point cos C, right? So then the difference is given by x tilde minus x at the point cos C, right? So that term vanishes, and I'm just left with this stuff here, right? Right. So I'm just going to take this out. Okay, so I'm also going to reindex these terms here. Okay. Sorry, that's an I. This is an I. Right. Okay. Yeah. So I've done some reindexing of actually everything. So I'm writing this as EKD because CI, right? So the J here gets replaced with an I. That's where it shows up. And here M get replaced with K. So this M becomes a K. The J becomes an I. This J becomes an I. And then the K gets replaced with J. Yeah. So, but anyway, it's like, so these are just dummy indices. It's like you can rename them however you want as long as you don't end up, as long as you map it in a one-to-one fashion, right? Okay, so anyhow, so that's the difference. Okay, so this tells you how it's like the vector field changes, right? In some sort of, this is the basis. So it's telling you how it changes as you vary the position. It's like by d cos ci, right? So this shows you, this gives the intrinsic change of x cos c as cos c is sort of changed by this perturbation d cos c, right? So, all right, and in particular, this is telling me how this term here is telling me how the cave component is changing, right? And this is telling me sort of in the ith direction, okay? All right, so, all right. Yeah, because, you know, this is the coefficient and then this is the basis vector, right? So this is telling me that for a fixed k, that's the cave component of this vector, right? And then this is telling you as you change, it's like the ith component, right? What's happening, right? So this quantity in the parentheses is telling you how it's like as you move in this ith direction, right? The cave component of the vector field is changing, okay? All right, so how do I denote that, right? So I can write down nabla, okay? I'm changing, moving the ith direction, and I want to look at the vector field, but the cave component of it, okay? So that object is this thing in the parentheses. Okay, so this is dixk. This is the kind of thing you would expect normally, right, on a flat space. But the point is that there's correction which comes from the fact that the basis vectors themselves are potentially changing as you move the points. So this is the connection term, ijk xj. All right. So this tells you, this is called the covariant derivative, right? This is called the covariant derivative. All right. And this covariant derivative, as you see, has two indices. There's an I and a K, right? And the point is that, if you recall, the reason why we introduced this as opposed to just the usual naive notion of a derivative is that the naive notion of a derivative doesn't transform in the right way for vector-valued objects, right? So So the whole point of introducing a covariant derivative is so that you have something which transforms in a tensorial fashion under changes of coordinates. And this covariant derivative does. Okay. And as I said, it's like nabla I x k is a tensor, which again means that it transforms in this tensorial fashion. Okay? All right. So now let's look at what happens if you add a second vector field to the mix. So you let y c be a second vector field, be another vector field. Okay. Then you can talk about not just the directional derivative in a particular direction, but the directional derivative in the direction of this second vector field, right? And the directional covariant derivative of x along y is given by the following. Okay, so nabla y x, right, is going to be just this object contracted, right? So this is the directional derivative in essence. It's like of xk in the ith component, in the ith direction, or e, it's like, or e sub I basically, right? So if you want to look at the directional derivative in y, you sort of take some appropriate weighted combination of these things. And what you do, again, is that you take yi nabla sub I xk, right? Yeah. All right. So you can think of this as being something like the dot product of y. It's like with the nabla operator, which you sometimes see. It's like, it's like in vector calculus, right? All right. So that is equal to yi. Okay. All right. So it's just this expression here, right? Well, technically it's this expression. Let's see. Yeah, so I'm treating this as actually a vector, right? The output of this is another vector. It's actually another vector field. And so I'm just going to contract it. It's like with the basis vectors as well. Okay, so this is the covariant derivative of x along y. And it is, again, a vector field. So, all right. So in the same way, you can also define covariant derivatives of tensors, right? So I should just remark that you can analogously define covariant derivatives of tensors. So we can sort of find sort of covariant derivatives of tensors, of tensor fields more precisely. right, by using the affine connection. To see how the basis vectors transform. Right. Okay. Okay, so all right, so I won't go into too much of the details about it, but suffice to say that you can use the affine connections in sort of an analogous way to how we derived the covariant derivatives. It's like to define the covariant derivative, the covariant derivatives of vector fields, to define the covariant derivatives of tensor fields more generally speaking. Okay, so for a scalar function, if it's a scalar function, it's like we don't have to worry about comparing scalars at different points. It's like it's a very natural way to compare scalars at different points. So we don't need an affine connection to do that, right? So for a scalar function, the change is measured using sort of just your normal notion of derivatives, right? Ordinary differentiation. Then you can ask, right, how this directional covariant derivative, it's like acts now on a scalar valued function, and it basically is just the directional derivative. So for the vector field y, right, it acts on the scalar valued function by directional derivative. So y acting on f is just a directional derivative. So that's y super I d sub I of f. So as before, it's like if you just did this naive thing where f now is on a scalar but a vector, that doesn't give you a tensor. And so if you're trying to, it's like measure derivatives of tensorial valued objects, right, then you need to use the covariant derivative instead. But scalars are sort of simple. It's like, and you don't need to evoke that more sophisticated machinery. It's like for scalars. But more generally, it's like for these tensorial values, you have to work with the covariant derivatives. All right, so let me just stop here for now.